Everyone, today we are going to see about in complex analysis Liouville's theorem. So the statement is a function which is analytic and bounded in the whole plane must be reduced to the constant. So consider the function which is analytic and also bounded. Analytic means there exists a limit and continuous, and it also contain a derivative. So it exists a derivative, that is the analytic form, and bounded means that function less than or equal to m. So if it is in the whole plane, then that the function must be reduced to a constant value. So we have to prove that. So let us assume that the function f of z is analytic. So the famous theorem about analytic is the derivative of a analytic function is also analytic. So if a function is analytic means the derivative of the functions also analytic. So from the higher order derivatives, we consider the form, that is fn of z equal to n factorial divided by 2 pi I integral f of zeta divided by zeta minus z whole power n plus 1 d zeta. This is the higher derivative form. Then what we do means we have to replace of our convenient, we have to replace z by z by zeta and sorry zeta by z and z by a. So we will get f n of a equal to n factorial divided by 2 pi I integral of f of z divided by z minus a whole power n plus 1 dz. So we are assuming that there must be a circle with radius a and center A and radius R. So we are equating that R gamma equal to that, gamma must be will be the circle, we are assuming that. So our modulus of z minus a equal to R, this is the form of circle. So what we are doing is, from the question we know that the function is bounded and there exists a constant value. So that the constant must be greater than 0. The whole function will be written as modulus of f of z is less than or equal to m. So for all z in C. So taking the modulus for this second equation, we get modulus of fn of a and the n factorial divided by modulus of I value is 1, so 2 pi, and we know that f of z dz can be f of z dz f of z can be written as m. So m divided by z minus a is nothing but r. So this is r power n plus 1 and into dz is nothing but circumference of the circle. So 2 pi r. What we are doing means we are cancelling out the common terms. So we get n factorial divided by 2 pi m divided by r power n plus 1 2 pi r. So we are cancelling the common terms and having one r we are cancel means we get the remaining terms, that is n factorial m by r power n. So our modulus of fn of a less than or equal to n factorial m divided by r power n. So from the Liouville's theorem we need only the case n. So in this we are, the Liouville's theorem is we have to prove that a constant. So we have to prove the one derivative, one form is constant means the all other form will exist. So we are considering the case n equal to 1 means we get let me check later. From the hypothesis nothing but unproved statement, it may be a false. The hypothesis will be formed by using the available data, and we are assuming that the form, it may be wrong, so it is an unproved statement. So from this statement we know we are considering that modulus of f of zeta less than or equal to m on all circles. We are assuming that this is the unproved statement. What we are doing means putting n equal to 1 means we get f dash of a equal to it will become m divided by r. So f dash of a equal to less than or equal to m divided by r. If we put r to infinity means this 1 by infinity is 0, so our value f dash of a will be 0. Then if we integrate means we get f of a equal to c, so our function is a constant. So we are proving that f of a equal to c, that the function is constant. So in Liouville's theorem we have to prove the function which is analytic and bounded means it must be reduced to constant. So we are considering the f of zeta as analytic and bounded, and we are replaced zeta by z, and we are proving that the function must be reduced to a constant. So this is the Liouville's theorem. Hope you all understand, and thank you.